from there.
All right. Thank you very much, Amy. Thank you all for being here. And I want to begin by thanking both Amy Sprang and my colleague Christy for helping put this together. I also want to thank PNNL for helping make this talk possible. So it's a great pleasure for me to introduce Joseph Williams, who is coming to us from the Pacific Northwest National Lab. And as many of you know, SPARC has an MOU with PNNL, and one of our joint objectives is to advance public understanding and education related to space technology, law, and policy. And as part of that mission, we have Joseph Williams, who is presently director of PNNL Seattle Research Center, which is located in South Lake Union, and also focused at the nexus of science, technology, and policy relevant to national security, energy, and the environment. Let me highlight a few things about his extraordinary background. He received both his Master's of Business Administration and his PhD in Management Sciences and Information Systems from the University of Texas at Austin. He was previously Governor Jay Inslee's Technology Policy Advisor, as well as the Economic Development Director for the ICT industry in Washington State. He's at present board member of Washington Technology Industry Association, WTIA. He's also chair of the Institute of Electrical and Electronic Engineers Seattle section. And most interesting to us, and what brings him here today, is that he is vice chair of the Quantum for National Security Technical Advisory Committee in 2022. And I understand, Joseph, that you will be chairing it starting in 2023 as well. The Pacific Northwest is becoming home to sort of the go-to location for quantum technologies. And what we have asked and what Joseph is going to reflect on for us today is really how those quantum technologies may potentially intersect with the space domain and what that means for us here in Washington State and for the global context going forward. So Joseph, with that, welcome to the SPARC Dialogues. We really appreciate you taking the time to be with us and look forward to the conversation. I'm going to hand things over to you.
All right, thank you. Let me share my screen. Amy, am I good?
You are good.
All right. So thank you, everybody. This is a absolutely fascinating topic. I will just tell you up front, I am not a physicist and nor am I a mathematician. So my interest in all of this is on the policy and economic development side. I appreciate, I'm going to go back there. I appreciate the physics, and I do spend a lot of time learning what a Josephson junction is and what a Hamiltonian is and all that, but I couldn't do the math to prove it out. So if you're going to ask very hard science questions, I'm going to have to get back to you later with those kinds of answers. What I'm going to cover today, I want to talk first about the investment ecosystem for space technologies, because quantum is super expensive and there's an investment-rich environment in space that's competing with that. I'll talk a little bit about quantum. I'll just explain what it is at a very high level. And then the three things I want to go into in depth are quantum computing and its impact on space, quantum communications and what's happening there in space. And my favorite topic actually is quantum sensing. And then this deck will be public, and there's some resources that will be available in the deck. Before I get too far into this, let me make a couple of call outs first. If you're not aware, or you probably are if you're on this call, but Seattle is the hotbed of space technology right now. It's super interesting to follow Stan Scholl's monthly postings of how many open jobs there are. Actually, it might be weekly, Stan, I'm not sure. But the number continues to just accelerate, and we are certainly a hotbed here. I also want to point out the University of Washington has its own quantum research center called Quantum X, and that PNNL also has its own quantum research center, which is based primarily in Richland, but we have some of that staff here. We also have the Northwest Quantum Nexus, which is a consortium. It involves Microsoft, UW, Wazoo, University of Oregon, PNNL, IonQ, and some other companies which are looking to develop the quantum ecosystem specifically here. Now, all that said, the confluence of quantum and space hasn't occurred locally yet. So it's not a Seattle phenomenon. It needs to be, but it's not. So that's one of the things that hopefully talks like this will stimulate, and we'll get some positive benefit out of it. Anyway, let's talk about space. So there's a lot of dollars being committed to space. As you know, Elon Musk and Jeff Bezos and billionaires are playing up there. But on top of that, there's all kinds of commercial entities which want to be in space for a lot of different reasons. So a lot of investment is going into the air, into space, and just operationalizing everything that's up there. There's a lot of work being done on space debris and how to track it. There's an enormous amount of effort to commercialize space, whether it's going to be with spectrum access, whether it's going to be 5G, which would be space-based broadband networks. There's a lot of interest in mining asteroids and things that are happening in space. We had a startup here in Seattle that was focused on that for a while. Actually, they might still be focused on it. And there's all kinds of supply chain issues. How do we get materials in and out of space? And what does that end up looking like? A lot of companies are in space doing Earth observation. Maxar, for example, does an enormous amount of work with satellite photography. They sell it commercially, and they do other things with it as well. And there's a lot of research being done, a lot of commercialization being done around sensing. Also around things like GPSs. I mean, all of our GPSs are space-bound, or most of them are space-bound. That takes economic investment, and so that competes for dollars. The other big aspect now has been the cybersecurity angle of space systems. So all of these objects are in space. They weren't designed to be all that secure from a cyber perspective. And so there's some risk there. And there are now adversarial activities. I won't mention any particular countries, but there was one this week that said if you attack our satellites, that's a declaration of war. And they meant a physical attack or cybersecurity attack. So a lot going on up there. And so it attracts investment dollars. Quantum has to compete for those investment dollars. And so the primary funders, and quantum is farther out. So we are, if you use the NASA model, we are in TRL 1, 2, 3 for what's going on in quantum and space. There's some commercialization going on, but very, very little. And so it's very hard to get venture capital dollars for TRL 1, 2, 3. So those dollars are coming from the government and are mostly coming from the government. So you're not seeing anything from Elon Musk or Jeff Bezos or Paul Allen's legacy on, how can we use quantum out there? They have people who are looking at it, but they don't have large production systems in place for this. To properly invest in quantum and space, we're probably talking $5 to $50 billion a year, year over year. And that's just not in the budget. All right, let's talk about quantum. So you might recognize Schrodinger's cat there, or some representation of it. The notion of quantum is about 120 years old, traces back to Max Planck's quantum hypothesis, which he published in 1900. The field of quantum mechanics exploded in the 20s and 30s. And by 1926, we actually had quantum chemistry emerge thanks to Schrodinger and what was going on with the cat. If you don't know the whole cat thing, part of quantum is this discussion. There was a big argument about whether there's observational impact on quantum state, and Schrodinger used a cat that was either live or dead to illustrate that. Fun fact, we nowadays, when you see the videos, the cat is alive or it's just dead like it's sleeping, but actually Schrodinger had it, I believe it was either being exploded or was being killed by radiation. So they've cleaned that up. So the story of Schrodinger's cat has gotten much more palatable. How important is quantum? So these are the Nobel Prize in physics only that have accrued to the quantum field. So 10 Nobel Prizes have been awarded in physics. When you think about what physics has been doing, I mean, we're talking plasma physics and all kinds of very interesting astrophysics, all sorts of elements of physics, and yet 10 Nobel Prize prizes have been awarded in this field. So it's a very, very important field. There are Nobel Prizes in chemistry and mathematics, which are also related to quantum, but it shows you that if you're a physicist, this is part of your bread and butter. There is no way I can explain qubits very easily, so I'll just give it to you this way. A bit is binary, it's either on or off. So it has a state of being on, state of off. You can collect them together. If you get 8 bits, you have a byte, and there's information which is stored and all that. Qubits are on, off, or both because of superposition. And I don't want to go into superposition, but it's another state. And so as you think about these qubits, they are exponentially more powerful than a bit. So when you're looking at computational power, if you can actually stabilize a qubit, you're going to get substantially more power. And I'll give you some data on that later in the presentation. The other thing is largely classical computers compute linearly, whereas because of superposition, a quantum computer will be able to sort through many different factors all at once to arrive at a more powerful solution or more potential. So there's all kinds of qubits. What you need to know is there's competition in the qubit field. So you'll hear about D-Wave, and you'll hear about IBM, and you'll hear about IonQ, and they're all different. They all use different technologies. They are using electrons or photons or atoms or something that act as qubits. 4 major categories are spin, which is a focus on the orientation, trapped atoms and ions, which are this energy state of the ions, photons, which are different. There's different approaches. There's polarized, path and time, and superconducting circuits are flow direction. Now, let me give you some names. So superconducting is what Google does. So when you hear about Google, like quantum supremacy, they were doing that on a supercomputer, superconducting quantum computer. Rigetti and IBM are also superconducting. Trapped ion is Honeywell and IonQ, and photonic is Orca, and I don't have a really good example of a spin that you would know about. Spin is really early in the TRL process at this point. Here's where it gets interesting. Each of these has advantages and disadvantages. And so if you're really going to become a quantum computing person, or you're going to be working with quantum workloads, you're going to have to match the computer, quantum computer that you want to the task that you're trying to optimize on, which is why Amazon, their offering is called Bracket, and they're headquartered here in Seattle. Bracket actually has 3 or 4 different kinds of quantum computers that you could schedule work on. Microsoft, through their Azure Quantum, has 3 or 4 different computers that you can schedule work on. So the intent is not to just do quantum computing, it's to match the work to the problem that you're trying to solve. So solving for chemistry is different than solving for, let's say, climate. So the word quantum has been kind of usurped in the popular literature. It now just means huge. You know, quantum, you know, I've seen quantum burgers somewhere that were just big burgers. But there's some interesting things about quantum. First of all, they're not stable for very long. The stability of the qubit is called coherence, and it's measured in time. And a good qubit keeps its state for milliseconds or microseconds. So thousandths of a second or millionths of a second. That's a good qubit. 5 seconds is amazing. And at quantum scale, 5 seconds, if you could get 5 seconds of coherence, that would give you 100 million quantum operations. That's quite a bit. MIT just announced that they've achieved a 10-second coherence, but they haven't applied it to computing. There are some claims out there of 30-minute, 40-minute coherence, but they're all specialized cases. We're really talking about general coherence. the concept of decoherence, which is when the qubit becomes unstable, they decohere instantaneously. As I mentioned already, UW is doing some great work in quantum. Your leading quantum material scientist is Kai-Mei Fu. She runs Quantum X. Our leading quantum material scientist is Marvin Warner, and he just published some work that he's doing in barium to try to make IonQ's computer more efficient. So we're all trying to figure out how we use materials to further the quantum mission. And if I were to look at a regional advantage that we have, I really believe it's material science. So if you look at the power that we bring from UW and PNNL and Wazoo and the companies that are here, it may end up that we are ground zero for the best in quantum materials. One logical qubit, which we use for computational purposes, may require 1,000 physical qubits. That's because of noise. There's a lot of errors in the creation of qubits. In order for quantum technology to actually become commercial, we're going to need millions of logical qubits. So 256 is sort of the high end right now, and we need millions. So let me give you some other context. Well, you can't see the chandelier yet, but most of what you see when you see a quantum computer is the famous IBM one that's a golden chandelier. That's actually a dilution refrigerator, but the computational device is at the bottom of that thing. And what that is trying to do is to get the temperature down to as close to 0 Kelvin as possible, because that's how you get stability with the qubits. But that chandelier is supported by 8 to 10 large racks of equipment. And that gives you 1,000 maybe superconducting qubit system. If you were to actually do this at scale, at quantum scale, it would be an entire New York City block to give you 1,000,000 qubits, and it would consume about 153 megawatts using today's technology. So big footprint, a lot of energy consumption, and it would cost about $5 billion to build one of these. So a lot of money. The other thing I'll mention is the quantum field is huge. It's extremely technical right now. In almost any meeting that I'm in, I'm basically talking to physicists or mathematicians or computer scientists. As we talk about, am I a quantum scientist? The next question has to be, in what field of quantum are you in? Because it's too broad to say I'm into quantum. It's got to be, it's not like blockchain, where if you say, hey, I'm into blockchain, pretty easy to understand what's going on. Quantum is not that way. You really have to dig far deeper into what they're actually trying to do. So why are quantum computers interesting? Well, they're interesting because if you had 1 trillion items today that you needed to sort through, it would take you on a standard set of commercial computers about a week to get one item out of 1 trillion. And 1 trillion is not outrageous. We're talking about 1 trillion weights for GPT, natural language processing models. So we're talking, these are compute intensive operations. If we put that on a quantum computer, and I promise you this is my only build, it would take you 1 second. So it's the compression of a week's worth of compute time down to 1 second. And the whole notion of quantum supremacy actually is we achieve quantum supremacy when the quantum computer can solve a problem that a classical computer simply cannot. And that's the threshold over which we're trying to jump. So quantum computers, that's the chandelier over there in the corner. It's always very pretty. And they actually are called chandeliers, but they are dilution refrigerators, basically. So we have to deal with the fragile state of the qubits. We have to figure out how to control the qubits. That's what all those wires do. Quantum computing is not the same as classical computing. So if you have a computer science degree and you know how to work in Linux, and you come to quantum and you say, hey, how do I get Linux to run on quantum? It doesn't run on quantum. So you need a whole new set of algorithms. So generationally, we're working with UW and other universities like Oregon and Wazoo to help them recruit quantum computing scientists, and we're doing the same. They're very, very expensive and they're not stable. They're almost like qubits because there's such a demand for them right now. And so they do a lot of jumping. Quantum computing is not going to work for most mundane computing tasks. The question I always like to ask is, what would you do with a quantum version of TikTok? Nothing, right? There's really no application there. The power of quantum computing is going to provide significant advantages for problems which are suited to the way quantum computers operate. We know this is going to be very productive in chemistry, in the discovery of new drugs. Goldman Sachs has a huge quantum group, and they're looking, well, they say they're doing it for economic modeling, but the real reason they're doing it is for arbitrage advantage. The government has a very strong interest in using quantum computing for weather forecasting and climate modeling, because these are very complex models and with millions and perhaps billions and trillions of factors that need to be accounted for, and that's well suited to what quantum can do. And then there's the cryptography angle here as well. Most of the news on cryptography is bad. Quantum computers will break the current RSA standards for encrypted data. So there's a lot of people scared about that aspect. So let's talk about space, because that's why we're here. Quantum computing is going at, so NASA has a very large group. It's at Ames and Goddard as well. Which are looking at quantum computing to optimize things like, how do we better explore space? Think about space, endless number of objects out there, not just planets and stars, but all kinds of other objects. How can we use quantum computers to better model that? The planning and scheduling of space missions is going to get more and more complicated as there is more and more stuff up there and more people competing to get their stuff up there. One of the things we're looking at the lab is, and DOE, is how can we optimize or maximize the lifetime of batteries used in space missions? That requires a staggering amount of simulation, and quantum computing is good for that. We might be able to use quantum computing and quantum sensing specifically connected to quantum computing to detect signs of life on other planets or to detect anomalies that are in space. Quantum machine learning is very new. It's an emerging field, but my prediction is we'll need machine learning to manage the complexity of quantum, because quantum computing is very complicated. So we'll basically need, if you want to think of it this way, AI to manage AI in the quantum context. There has been an idea kicked around, because we have to do these at very low temperatures, 0 Kelvin is the goal, that we could build quantum computers in space, and that actually doesn't work for two reasons. One is space actually isn't that cold. I think space is 3 or 4 Kelvin, and it literally has to be down to the micro Kelvin level. And the other problem is there's a lot of radiation in space, and qubits get destabilized by radiation very easily. So that's quantum in space, just in general. Let's talk about quantum communications. So Albert Einstein famously called quantum communications spooky action at a distance. Current commentators like to just say it's bizarre. So the way quantum communications works is not consistent with your understanding of the way the universe works that you've gotten from watching Star Trek or Star Wars, and I'm in the same boat. Quantum communications is very sensitive to environmental interference, as I mentioned. The way it kind of works is they need to have 2 photons which are entangled, and the 2 photons, when they're entangled, actually allow you to have instantaneous communication based on things that are happening with the state of one photon. It immediately impacts the other, and I mean immediately. One of the ways they do that is they fire a quantum laser at a crystal that releases 2 identical photons which are entangled. You could keep one of the photons, send one somewhere else, and you'd be able to communicate by the entanglement of those photons. There's a lot of physical limitations to how far away these can be and how long the entanglement will be coherent. There's a lot of technology being invested in building relays, so it's the way to connect quantum states together so you could extend the distance and perhaps preserve the state. Timing ends up being super critical. So if you go to Boulder, NIST has a center there. It's kind of attached to the Atomic Clock Project, where they're working on making the most precise atomic clock possible using quantum technologies. And that's going to be used in quantum communications. Space-based quantum relays have a lot of advantages over terrestrial. For one thing, there's not a lot that's going to happen in the pathway as opposed to terrestrial. But the other is it's more predictable. And then the other side of quantum communication is we're pushing on what is being called now post-quantum cryptography, but it's a way to secure your communications so that they can't be intercepted. So one of the most famous quantum scientists for quantum communication is Han Jianwei, and he is the father, if you will, of quantum science in outer space for China. And in 2013, the government gave him a massive uplift of his research funding. And by 2016, China had launched the Messiah satellite that sent 2 entangled photons to 2 Chinese cities 700 miles apart. That's actually pretty remarkable. They used it for doing quantum key distribution, which is a cyber security thing. They proved that these entangled particles could survive the journey. And it's important to know that it was just a proof of concept. They didn't actually deliver any information. They've updated their work since 2016. The longest connection that I'm aware of right now is between Beijing and Vienna, which is 4,400 miles. The connection's not terribly practical. It's actually outrageously expensive per byte that you're sending, because the best transmission rates you can get are a couple of kilobytes per second. And that's even worse than modem speed if you're old enough to remember modems. Where's the rest of the world at? So the US is working in quantum lasers. That's kind of our big play. NASA's partnering with MIT's Lincoln Labs on what that would look like. That started in 2018, and we're going to use the International Space Station as a quantum communications relay. Argonne National Lab, another DOE lab, is talking about how to build space and terrestrial platforms to support a global quantum network. Goddard and Ames are working on how we use quantum to support space missions. Also, a very interesting paper that Ames published last year, I think it was Ames, could have been in Goddard, might have been both, on how quantum can be used to create a network connecting the moon with the US in some sort of real time. So you don't have the delay that people envision when they're making space movies. The European Union is taking this very seriously. They're investing 6 billion euros into its own program. That's slated to start in 2024. It won't be complete until 2027. The UK kind of is doing its own thing since it's not part of the EU anymore. It's invested $500 million in OneWeb, which is the failed, well, not really failed, but it's the satellite consortium that was being driven out of Japan for a while. That has about two-thirds of the satellites are up in the network. There's 214 of them that are yet to go up. I don't know if you know this, Stan probably does, but Russia launches the OneWeb satellites, so they're not going anywhere right now because of what's going on in that part of the world. Where is the US? Well, we funded the LCRD program, the Laser Communications Relay Demonstration. That launched in December. That's going to end up, I haven't seen the current data, but it's supposed to go geosynchronous at 22,000 miles. I haven't heard anything bad, so I assume it's actually working as it's intended. It's connecting California to Hawaii right now. The focus is on weather impacts, and they're testing laser communications. There's a set of experiments in the Illuma-T platform that will commence this year on sticking a kind of an ugly box on the side of the International Space Station to support quantum end-to-end laser communications that will support quantum communication. MIT Labs is doing some interesting things, as I mentioned, and I'll point out that Marconi 2.0 is an idea that's being developed right now to connect the US, or North America anyway, to Europe, and NIST and the National Reconnaissance Office are both involved in that process. Quantum sensing, super interesting stuff. So we measure things in very strange ways. We measure things with measuring sticks and lasers and things like that, but we don't measure at the atomic level very well. And at the subatomic level, we don't do much of anything. We have a hard time measuring subatomic phenomena outside of a controlled lab environment. When it actually commercializes, we'll be able to use quantum sensors to look at things at the atomic and subatomic level. And effectively, if you want to kind of think about it, we'll be evaluating things at their gravitomic level through gravity rather than in their physical manifestation. So quantum sensing, the way it improves on what we're doing now is it measures motion, so acceleration, rotation, gravity. It measures electric and magnetic fields, and it helps with imaging. Because of entanglement, we can make very, very precise measurements from space. And the things that are going to be super interesting will be the way we do climate analysis. We can actually evaluate. We have a volcano somewhere here in the state of Washington. I can't remember which one, but the magma core is rising, and using quantum sensors, we'll get a much better look at what's happening there. Not only will we be able to see earthquakes, which are not otherwise measurable, but we might be able to predict. And then there's all kinds of interesting things that will happen with quantum sensing underground and underwater. Underground could be the discovery of archaeological sites that have been buried 100 meters below the surface. Underwater, I mean, it's possible that quantum sensing could completely illuminate the ocean, and you could see where every fish is, or every fiber optic cable, or whatever you think is in the water. I can't comment beyond that. Who's interested in quantum sensing? Super interested is the government. They want to use quantum sensing for military and defense. The Air Force is investing massively in quantum sensing, as is NASA. The national labs, I already mentioned us, and universities heavily involved in quantum sensing. A lot of commercial interest in quantum sensing as well. Some of that revolves around more accurate timing. There's a lot of fear that our global GPS system is vulnerable in the way it's been deployed in space, and quantum could be a replacement for that. When you talk to folks at Exxon, or you talk to people at large mining operations, they're super interested in, they use ground penetrating radar right now. Quantum will give them better information. Quantum sensing will help in the site preparation for construction and the monitoring of infrastructure. As I mentioned, it's going to be used for archaeology. And one of the emerging interest areas is out of California, which is in Colorado, both of which are super interested in what's happening to their water table. They can't measure everything, and they think quantum sensing will help with that. So quantum sensing right now, it's mostly in prototype, but the prediction is that we'll be 3 to 5 years away from limited commercialization. I want to emphasize again, this is all very nascent because what I did was we had our librarian pull all the documents that have been published in the last 2 years on quantum sensing, and you can see the total count for the US is 12. So not a lot of research papers being published on quantum sensing in space. A lot more on quantum sensing, but at the intersection of quantum sensing and space, it's an emerging field. And if you look to the pie chart, you can see that the disciplines that are most interested in quantum sensing in space are still physics and astronomy. And engineering, no big surprise, and computer science and materials and math, all kind of equally interested as well, because they're all trying to solve fundamental science problems that exist here. I do want to call out, there is a methane leak over the state of Louisiana right now. And it was detected by satellite on January 21st. It's leaking 100 tons of methane per hour. And here's the fun part. They don't know the source of the emission. So they've gone to all the methane producers in the area saying, hey, do you have a leak? They've all said no. So what could quantum sensing do in this context? It would actually give you a way to specifically identify where that methane is coming from. And that's not currently possible with the technology that we have. So here's a bunch of resources. This deck will be available. I'll point out UW has a very nice website for QuantumX. We do as well. The Department of Energy is funding billions of dollars worth of quantum research through its National Quantum Initiative, the NQI. We're super interested in developing a quantum workforce plan here for the state of Washington. You may not know that Commerce Secretary Lisa Brown made an award to the WTIA to begin the development of a quantum workforce plan for the area. And since I sit on that, I'm going to try to get them to pay attention to space as well. And then there's this really nice video, it's very short, that explains the difference between a quantum computer and a classical computer that I would refer you to. And with that, Amy, I am done.
Joseph, thank you very much for that. Amy, I can see things. Sorry, we had a little bit of a technical hitch, but I think we're good. Joseph, thank you for that excellent overview and for the connections also to space. And I think one of the things, I will leave the hard technical questions for the physicists and the astronomers who are here. And if you do have questions, please go ahead and put them in the chat. Let me ask you, Joseph, about the emphasis on workforce development that you had talked about. And can you say a little bit more about ideas that are bringing, that would be helpful to the university as we also think about positioning our workforce in that direction, particularly related to space? So this is some broad ideas about workforce development in Washington State related to this intersection of space and quantum.
So there's a national initiative called the Q through 12 Education Initiative, and it has a lot of stakeholders at this point. It's being pushed by the White House Office of Science and Technology Policy, but there's a lot of DOE labs involved in that as well as the NSF. And the idea is to try to attract more students to the quantum field, which would ultimately produce more physicists, likely the way it's set up right now. And that starts in literally kindergarten all the way through 12. So there's an entire curriculum. What they're developing now is, okay, you've gone through this program and you're super interested, where do you go? I mean, what's the next step in your career? Do you end up at a University of Washington, or do you go to Seattle Central Community College? And are they connected, and what happens there? I will tell you, this is a hard field to be a researcher in if you don't have a PhD. Eventually, there's a huge shortage. And as you all can appreciate, it takes a very long time to get a PhD in physics, PhD in material science. And so there's been a lot of conversations in what the off-ramps might be for somebody who maybe is a craftsman. So they're good at electrical wiring, or they're a tradesman, or they are undergraduate computer science majors, or they are maybe involved in the operational side where they don't need to have the deep research credentials. But since this is a very young and emerging field, well, it's 120 years young, but the commercialization of it is nascent. Really, it's being dominated by the PhDs or the people who are in PhD programs who dropped out to commercialize. So what the state is doing is basically saying, well, how do we explain quantum? So that's teacher training. So how do we go out and give teachers the skills they need to explain what quantum phenomena is and how it works? And then how do we attract and retain students who would be interested in STEM in general and then quantum specifically? So WTIA, as the manager of that program from Commerce, is starting to look at the landscape to try to figure out how to best do that.
Fantastic. Thank you so much, Joseph. I think that's very helpful, and that's something that we would love to hear about in the context of both Spark and the University of Washington more broadly. I have a bunch of questions already, so I'm going to start reading them out. And let me begin with this question by, I believe this is Sajjad Moezeni. Is there any plans to experiment QKD with NASA's LCRD, or is it just for classical optical communications?
No, there is a plan.
There is a plan. Okay.
Yeah, if you actually Google quantum key distribution and the NASA program, there's some preliminary work that NASA has published on that.
Mm-hmm. Okay. Another question, I think, sort of not looking, I think this is from Ellen Caswell. I think you had spoken about quantum sensing sort of focused on the Earth, but sort of looking out, does it also help with detection of, let's say, extraterrestrial life or microbial life off planet?
It would, Alan. So it's not just downward facing, if you will. That's not really meaningful in space. It would allow you to take a pretty good view. If I can deliver the photon, I can manipulate it in such a way that I get information back from what's happening in space.
Mm-hmm. There is a question from, it's not a question, more a statement. This is from Mark Polyakov. I've heard HRL labs are working on spin-based quantum computers, quantum dot. Can you comment on that, or do you have any thoughts on that?
Is the questioner asking about what quantum dots are?
I'm not sure. The whole thing reads, I've heard that HRL Labs is working on spin-based quantum computers, and then in parentheses is quantum dot. So if you could actually explain to us what quantum dot is.
So spin-based and quantum dots are describe similar phenomena.
Mm-hmm.
I'm not aware of a commercial
Mm-hmm.
quantum dot, quantum spin computer. Doesn't mean it's not there. I'm just not aware of it.
Mm-hmm.
And so I don't know where they're at in terms of their development cycle. But they use the rotational aspect of the photon in order to create the quantum state. Beyond that, you're past my physics limitation. I only got through physics 1, A, B, and C.
This is from Adrian Guzman. Have you worked with other field groups like George Church at Harvard, for example?
Us personally?
Yes.
Yeah. So so the lab, we're the government's lab. Mm-hmm. So we primarily work with the Air Force, the Department of Defense. We have partners, university partners. University of Washington is obviously one of our big partners. We talk to researchers at Harvard and Columbia and Princeton and the like, but actually outside of the state, I think our primary relationship is with the University of Maryland right now.
Mm-hmm. Mm-hmm. So just on that comment, you talking about partnerships. I know that you're sort of focused on UW and UMD, as you just said. Are you also at the center of international partners or building out international partnerships? Because there are other places that are also investing a lot in quantum. So just kind of curious about whether you have international partnerships.
So apart from space, yes. So I actually personally am involved, or I attend, they let me attend the Amsterdam quantum work group. We work with the UN on some of their quantum programs, QEDC, to which PNNL belongs, also UW belongs, which is the Quantum Economic Development Consortium. They are internationalizing, so they are originally funded by the US Department of Commerce, but they've decided that there's so much fractionalization of all the quantum experts that in order to bring everything together for a solution, you really need to go international.
Right.
In the quantum for national security, not so much. So in that space, we're still pretty US based,
Pretty US.
US focused.
So in this case, this question from Mara Zimmershield, I think is an important one. Are there any other national labs working on this?
Yes, many. When you have billions, hundreds of millions and billions of dollars that the DOE is making available, you get all the DOE labs excited. To my knowledge, there's a dozen of the DOE labs that are involved in quantum research, but also the federally funded research centers are called FFRDCs. So there's the Applied Physics Lab, for example, on the UW campus. They're an FFRDC. I'm not aware that they're doing quantum work, but Johns Hopkins, which is their big competitor, is. And so their APL is heavily involved in quantum research, as is the Air Force Research Lab, AFR, or the Office of Navy Research, ONR. In fact, the only group I know of that's not doing any quantum research right now specifically is Army. They have quantum research, but they don't have an office that's specifically attached to it.
Interesting.
And our intelligence communities are heavily involved in quantum. So everything that ends with an A.
Good. This is a question from Brian Harvey, who's asking, I guess, what app is the most promising in related to space at the Space Quantum Nexus? I think you were spelling that out as part of your presentation, but perhaps
yes,
those issues.
So there are no apps yet. We haven't got to that point. But if you're talking about the application area, the one that is at the best intersection of commercial interests and government will be quantum sensing. So I think quantum sensing will probably precede quantum communication. And quantum computing is applied to outer space. Quantum computing is expensive. I don't know if I mentioned it, but a quantum computer is $5 to $15 million, and then $2 million a year to maintain it. So at the moment, there is not a quantum computer in the state of Washington. There will be soon, but there's not now. And so these get rationed out. And so they're like supercomputers in that regard. So I just don't think they'll be used. They're too expensive to be used for mundane kinds of things. I think they'll do high priority commercial development first.
Joseph, if I could just follow up on that a little bit. I think your presentation is very clear that quantum sensing is a potential commercial. But given the interest in sort of having secure communications, you're not seeing the same possible commercial solutions for quantum communications. But do you see a role for that in the DOE labs and other university centered? Maybe not commercialization, but given where we are in geopolitics, there must be a huge push to sort of develop that aspect.
By government.
Yes.
So yes, NSF has funded a lot of work in quantum communication. So has DOE. Harvard's very involved in quantum communication, as is in our region, the University of Arizona. It's doing a lot of work in quantum networking and quantum communication. It's a consortium. So there just isn't the talent yet at the University of Washington campus, for example, to do quantum communication. That's going to have to be a hire, right? That needs to be made. Same is true for us. We actually aren't very strong in quantum communication at PNNL. We're aware of it, but it's an emerging field. Space-based quantum communication is probably going to be led by Sandia National Lab, but Argonne is heavily involved in that as well. Although if General Finnan is very aggressive, maybe we'll take a leadership role.
I do want to step in a little bit on that point about the University of Washington's work in quantum. We do actually have hiring going on in this area right now. There's a cluster hire in quantum.
I've heard that from Kaimei. She's very excited about all the interest that President Kelsey has put in quantum.
Yes. Yeah. So the College of Engineering has a cluster hire in this area going on right now.
Awesome.
Yeah. Stan has a question here as well. So Stan's question is, how is the U.S. positioned competitively, let's say, relative to the rest of the world? When it comes
Stan, you know I can't answer that.
You can't answer that, Stan. We had this conversation. Who's ahead?
Just go with the popular. What's the popular opinion out there, Joseph?
If you were to go Google this,
Yeah.
you would see that the two major players are us and China.
Yeah.
And who's in the lead? That's,
Yeah.
depends on your metric, right?
Yep.
Europe is playing catch up. There's absolutely no question. Surprisingly, you guys all might be surprised by this. Australia is emerging as a big player. They're doing a lot of work in quantum silicon and on the materials side. So they're punching way above their weight right now. The thing that kills me is in North America, actually Toronto is one of the big centers for quantum. So as we try to build a competitive ecosystem here in Seattle, we're not just competing with DC and Austin, Texas, and the Valley. We have to compete with Toronto and British Columbia. Vancouver has a big quantum ecosystem as well.
I'll send around an article. I used to write for Forbes, so I did something a long time ago on China's quantum. I think I sent this to you, Joseph. I'll send it to the rest of the group. It's a little bit old, but you can kind of get a sense for how this works out in the geopolitical context.
Yeah,
well.
you can talk more about that than I can.
I think I better not say anything either, Joseph. This is your talk. I do have another question from Alan Caswell. He's asking, could you name a good quality, but not too techie article, book, website that takes a deeper dive into how quantum works?
Is the question being asked by a scientist or by somebody who's not a scientist?
I think I am not sure, actually, to be honest. Just a good.
Hi there. Not a scientist, background in IT, undergraduate work in IT, so been involved in IT my whole life, interested in how quantum works and how a programmer type person or whatnot would use it, employ it, understand it.
So Alan, I have a great answer for you.
Mm-hmm.
IBM has amazing resources online
Okay.
for quantum computing, which kind of promotes their Qiskit environment, right? Microsoft has an amazing portfolio online, and Amazon Bracket's starting to put theirs online. So rather than buy a book, I would go look at what they have, and then they have these really nice videos, nice high-grade production value videos, which I think are super interesting.
Okay.
So that's what I would do. Quantum Key Sharp, if you were to learn Key Sharp from Microsoft, for example, it's not that hard. It's not, it uses Jupyter notebooks. It's just not that hard.
Okay.
And there is a question about not just about UW, but also to have deeper conversations for partnerships in quantum research. How might we go about that in the context of the of PNNL, for example, with the public? Do you have engagements? Are you able to connect to you? How would you like that to proceed forward?
So we're in the early stages of that. That would be driven by General Finnan or Sarah Fraser or myself talking with UW. And then we already have an agreement with UW through the NQN. And so the question would be, I actually was talking to some folks over at the Jackson School who were like, should we have policies about outer space and quantum? And yeah, maybe. But of course, it comes down to, do you have a faculty member who's interested? Which makes it more difficult.
Yeah, I think that's right. So it has to be in many ways faculty driven. So
Yes.
the enterprises are on campus. I am not seeing any other questions, but General Finnan, did you want to weigh in on the possibilities that you see for quantum moving forward, as Joseph was talking about? If you wanted to make any comments, I don't know if she's here. She's here. I see that she is here.
Yeah, no, I mean, I think there's lots of opportunity out there because this is an important field. And so, I mean, it's one of those game changer technologies. For instance, if you start thinking about communications, you think about, well, if I get quantum, if I'm first to get quantum, does that mean I secure my data better and I have more access to other people's data? And what does that mean to me if I don't want to have other people have access to my data? So it really is a race. Same thing with sensing. right? What if all of a sudden the seas are transparent? If I can use quantum sensing and I can see to the ocean floor and I know where every fish is, what does that mean for my national security and for other people's national security? And what does that do to, say, the deterrence equation? So, you know, I think quantum is a game-changing technology, and that's why there's so much interest in it. And I believe that will carry right out into space. And I think there's going to be a ton of opportunities.
Thank you so much, General, for those comments. I also feel the same way as you, and I think work on this as it begins. Joseph, thank you for giving us a great overview. We look forward to continue partnering with you and to sort of building bridges, both on the STEM side, but also on the law and policy side. Thank you, everybody, for joining us today. Thank you also to Salal Credit Union for sponsoring these talks, and also want to announce that we have Jason Hartwig, who will be joining us on April 14th, I believe, the next. Is that correct, Amy?
April 11th at
Sorry.
4 p.m. So it's a different day of the week and a different time, but we'll send out an announcement.
Thank you very much for joining us, everybody, and we look forward to having you with us again soon. Thank you, Joseph, again for an excellent overview.
Thank you.
Thank you.
Yes. Bye-bye. Bye-bye.